Okay, so I hope everybody can hear me now. Well, thank you very much. Thank you for inviting me to this tutorial on fine-grained recognition. Today I'll talk about higher order pooling in the context of fine-grained classification. My name is Pitor Koniusz. I'm a senior research scientist at Data 61 in CSIRO and at the ANU. So firstly, I'll talk about statistics, and I'll motivate it from the point of view of the Kershaw dimensionality, which will lead me to the concept of burstiness, pooling, and then I'll talk about a characteristic function in order to capture statistics of images, which naturally leads to higher order pooling. I'll talk about power normalization and non-Euclidean distances very briefly. I'll present a typical second-order fine-grained pipeline, and then I'll talk about different variants of power normalization in relation to the heat diffusion, and then I'll give more examples of second-order pooling applications in few-shot learning, action recognition, detection. In order to build a robust classification system, one has to deal with capturing statistics reliably. Capturing statistical moments from 0 to infinity can capture entire data distribution. Of course, mean captures first-order statistics, covariance can capture second-order statistics, higher-order tensors would capture higher-order statistics. But the issue with that is that with the low number of samples, one has to obtain somehow the robust statistics. For third-order tensors, the number of coefficients grows cubically with respect to the dimension, the number of features, which results in poor estimates. Which brings me to the notion of the burstiness. Which is a property that visual element appears more frequently or less frequently than statistically expected. This is a source of nuisance variability. So burstiness, in fact, it is a form of signal, but we don't like it. Just to give you an example, imagine that you train a classifier on some foreground versus background, you obtain statistics. Over here, you train SVM. But at the test time, maybe your foreground differs a little bit. So you have a larger area of leaves or background. So those statistics change, there's a drift, and this time SVM fails. To deal with that, we typically use so-called power normalization. I explained in a moment. But the notion of the feature burstiness was coined by Jagot in 2009. An idea actually predates to, I think, 2005 or maybe even earlier. So the key idea is to apply power normalization, that is square root normalization on features. And over here, auto fed it into the intersection kernel, and they obtain very good results. In fact, power normalization, the simplest form is just raising to the power of gamma the coefficients of some vector psi. And this time, whether the area of the foreground and background changes or not, the statistics are quite similar. So the power normalization, what it does for the very rare features, it boosts the impact, and for very frequent features, it dampens the impact. It equalizes statistics to some degree. And this is good in fine-grained recognition because we often try to detect very rare visual features. For instance, we try to detect a beak of an animal, and we somehow want to dampen the impact of background features. So power normalizations make the estimation of statistics robust to the bursts of features. Given finite data, of course, if we had infinite number of examples, all the possible configurations of the bursts, then we can learn it from the data, but this is rare. So I want to talk about pooling in general, firstly, because those power normalizations, they often in one way or another are done during the pooling step. So just to give you an idea, I imagine that you have some patches or maybe feature vectors extracted from convolutional layer. You can encode them by some function f with convolution. You obtain features psi. In this direction, we have the spatial mode. In this case, it's just a 1D illustration, but of course you can extend it to 2D. Now along the rows, function G performs some summary, and this summary essentially is pooling. Once we get a signature of an image, we can pass it to the classification, to the classifier. And the role of pooling is to, in one way or another, deal with statistics of features. So pooling can, for instance, realize some invariance to repeatable visual stimuli, or sparsify features, or perform some form of feature detection. For instance, average pooling performs count of a given visual feature in an image. In contrast, maximum pooling acts more as a detector of a visual feature, and it'll become clear in a moment why. But there's also a family of functions that, in one way or another, they are inspired by likelihood. So, for instance, this pooling called maxx is again a form of power normalization. It is a probability of at least one feature occurring in a set of features, and it is given by this equation. And there are several others, but they do very similar job. So just to illustrate that, imagine that we draw 1,000 regions from an image. Each region is described by 10 features, and they are drawn from some IID distribution. It turns out that the maximum pooling is a lower bound of this other form of pooling called ExaPro. This maxx pooling over here is a lower bound of ExaPro. But what is important is essentially this nature of curves here, which saturate very quickly. So in this X direction, we just sorted bounding boxes by the average pooling response. And over here, we can see that the moment 1 out of 10 features responds strongly or reliably, those poolings like maximum and the probabilistic ones, they very quickly saturate. So they tell us, okay, we've detected the feature. Now I wanted to move to tensors because in order to capture higher order statistics, we essentially need to use some tools from algebra. So first order tensors are just vectors. Second order tensors are matrices, for instance, covariance matrix. And then obviously third order and higher order tensors have a larger number of modes. What is important is the definition of some outer product for those tensors. So for third order, just to give you an intuitive example, if we have 3 vectors, we want to obtain the outer product to form third order tensor. Imagine that we simply take outer product of u with v, we vectorize it, then we take its outer product with z, and then we reshape the output matrix back into the tensor. And this is as simple as that. The reason why I'm talking about it is because those tensors, they emerge from characteristic functions. So if you want to compare images, video, sound, text, one wants to capture some distribution of patches or local descriptors, receptive fields in an image or document. So one can write a characteristic function over here where X are patches drawn according to some distribution. And after expanding the characteristic function over here by plugging it into Taylor expansion, after crunching mathematics, we arrive to equation over here where we have summation over order 0 to infinity, and over here a tensor emerges. So essentially those tensors, they capture in one way or another different order statistics. In my experience, third order tensors are more informative than second order tensors, but the issue is, as I mentioned already, the number of elements in third order tensor grows cubically, which is not good. It's hard to reliably estimate them. The typical fine-grained pipeline that uses high order statistics essentially follows this figure over here. So again, imagine that we have some descriptors X, we encode them with some convolution F, we obtain features phi, we stack them into matrix, we perform out a product of some order R, and then along rows we perform pooling with some function G. Most of the pipelines really follow this type of design. Now, I wanted to explain what is the connection of second order statistics and power normalization to non-Euclidean distances. So in terms of power normalization on covariances, the idea is very simple. When we have some covariance V and we raise it to the power below 1, for instance, 0.4, what happens is that the eigenvalues start being equalized. And of course, the lower the power value, the more equalized are the eigenvalues of the covariance or autocorrelation matrix. What it means is that we essentially perform detection in the spectral domain. In contrast, non-Euclidean distances really they measure the distance on the geodesic path. So we have the cone of positive definite matrices, some 2 points, and then we measure the distance on the path on the manifold. So those two things are different. There's a large number of papers that worked on second order statistics. So one of the earliest is covariance region descriptor. And this descriptor uses log Euclidean distance for classification. Another distances used in the literature are affine invariant Riemannian metric. And then we arrive to power Euclidean matrix, which essentially realizes power normalization over here. This component here is nothing else as a power normalization feature map. And again, some people argue that there is a connection between the two. And in fact, in limit there is. For instance, if gamma tends to 0, one can show that power Euclidean distance, in fact, converges to log Euclidean. But in my opinion, it doesn't matter really, because the value of gamma, typically for the good classification performance, has to be greater than 0.3, maybe it's around 0.5. So this equality here doesn't really hold. So there is more on this topic in our previous tutorials over here. And then, of course, we host, my colleague hosts an archive of papers. If you're interested, you're more than welcome to have a look at those. Now, I just wanted to explain again how typical fine-grained pipeline looks like. So simply we have an image, we pass it through some convolutional neural network, or we can pass the patches. We can even pass their positional embeddings. We obtain features phi. Again, concatenate with positional embeddings. We perform out a product over here, and then we perform some pooling with function G or G hat. So here by G will mean element-wise operators that operate just on rows of features, and by G hat will mean spectral. Once the pooling is performed, one just passes it into the classifier. And there's a huge number of those power normalization functions. So we studied them. For instance, we divided those operators into element-wise, spectral, then element-wise operators can be performed. Element-wise operators can be divided into non-negative or positive negative. They can be divided into those that work on positive semi-definite matrices or indefinite ones in Crane spaces. And most importantly, recently, we also noted that, in fact, one can perform power normalization by looking at covariances as being graph Laplacian matrices. And it turns out that there is a correspondence between heat diffusion process and power normalizations. So over here, just a quick example of those pooling functions. They operate on some spectrum P. And over here, we have the ones that operate on the Crane spaces. Over here, we have the closed form of those operators. What is important is essentially they push forward characteristics. So whichever pooling it is, really they perform very similar job, whether it's a gamma pooling or max exp. As you can see, the moment the spectrum is detected, the curve really boosts it and saturates at some value. And then, of course, if we work in Crane spaces, then we want to also deal with the negative spectrum. What is important is that this is a behavior of detector, or spectral detector, if you like. So just to reiterate, for instance, if we use element-wise pooling, this function over here really acts as a detector. And then for a cocurrence pooling, if we want to detect some cocurrence of phi n with phi prime n, it turns out that the function really, under assumptions, for instance, that features are drawn from Bernoulli distribution, it has the same form. So maybe I'll skip the proof over here, but what is important is that many papers in computer vision really use some form of power normalization. So for instance, root sift, Fisher vectors, bilinear pooling, and many other fine-grained classification pipelines use square root in some way somewhere in the pipeline, but they don't perhaps study the role of that in depth. And over here, I just wanted to briefly explain the connection between power normalizations and heat diffusion. So assume that you have a structured multivariate Gaussian distribution with covariance matrix M. And this matrix M has, by design, associated with it a graph structure. And it can be described by so-called precision matrix, which is an inversion of the covariance. It essentially gives us a loopy graph Laplacian. Assume that the spectrum is normalized, and then if you write a heat diffusion function k parameterized by some time t, you can look essentially at again at the function in the spectral domain. So this beige function over here is a heat diffusion. The blue one is the max exp pooling, and then the red one is the gamma. And for some parameterization t, this heat diffusion curve here can essentially touches the other two functions. It's a lower bound. It's very easy to see that because it looks similar, it should essentially act also very similar to power normalizations. And here is the illustration of that. So imagine that we have some spectrum that follows a beta distribution. We can pass it by this type of pooling. The moment we set a parameter really high, most of the eigenvalues tend to concentrate around 1. So they were essentially rearranged from this spectrum into this spectrum over here. For the gamma pooling, the same thing happens. And then for the heat diffusion, you can see again that essentially as the T approaches 0, which means we're trying to reverse heat diffusion, most of eigenvalues concentrate again around peak of 1. The beauty of this particular pooling operator here is that it can be realized just by matrix-matrix multiplications, which means that it's very efficient on GPUs. And whole heat diffusion over here can be approximated by the function over here. Again, the derivative has closed form, which relies on matrix-matrix multiplication. What is even more interesting is that the one can control the level of this or impact of this power normalization by parameter eta, and the complexity of this method is, essentially scales sublinearly with respect to parameter eta. And this can be achieved by exponentiation by squaring. So this is the algorithm. Just to give you an idea, typically for fine-grained recognition, people try to compute approximate matrix square root with Newton-Schultz, which roughly, for typical parameters, number of iterations k equal 20, it requires 60 matrix multiplications. In our case, for typical eta, this can be done with 8 matrix multiplications. And the same story can be emerges in the backpropagation step. What is important here is that the matrix square root essentially is a specific realization of power normalization, where we raise the matrix to the power 0.5, but this is not always optimal. So this algorithm here lets you control essentially that. Okay, so just wanted to show you some results very quickly. For flower 102, using spectral pooling is better than using element-wise pooling. And of course, those are better than just bilinear pooling. The same can be observed on MIT, on fine-grain food 101. And we also tried those ideas on graph classification. So we took graph isomorphism network, and then we applied different operators. And again, this fast max-exp operator appears to work better than element-wise operators over here, and also better than just using Newton-Schultz, for instance. Now, I just wanted to talk briefly about applications. So, example one interesting example is fine-grain image recognition. Imagine that you have so-called support images, query image, which form episodes for training. You pass them through the network. For each of the images, you form one can form a second-order matrix. Those matrices can be concatenated, so query and support matrices are concatenated with each other, passed through some pooling, passed through similarity network to learn whether query and support images belong to the same class or not. And over here are results. RelationNet is a first-order network. SOSN is a second-order network, and this is fine-grained image OpenMIC. So from the results, I mean, it's clear that the boost is quite visible the moment we go from first to second-order statistics. And then as we increase the resolution of images, again, there's a further boost. The same can be observed on other fine-grained recognition images, so on flower 102, food 101. Now, those tables contain many results, but the important message here is that if the network is pre-trained on one data set and want to fine-tune it, it turns out that the spectral operators are better at it. if we train the network from scratch, element-wise operators are enough. And this behavior actually showed up on several data sets. And after studying what happens there, we concluded that the spectral form of this power normalization here, essentially it reduces diffusion of the signal in autocorrelation matrix. What it means is that when we try to adapt the network to some new concepts, it essentially results in a better utilization of filters, because we decorrelate different feature coefficients, different channels of features from each other. It means that as we update, only few of them get updated, not all of them. I think this is a very interesting result. Further examples, one can use second-order statistics to model prototypes for few-shot learning. So, for instance, images from the same class can be represented by the affine subspace, and then one can perform querying, looking whether a query is closer to one or the other subspace in order to perform classification. So again, comparison, prototypical networks are first-order network, and PSN essentially uses the affine subspaces, which are second-order network. The boost is visible between first and second order. Another example is action recognition. So imagine that we have skeletons, we have some 3D coordinates, we perform the coding, embedding, we compute third order outer product, form third order tensors. Now one can perform a power normalization by applying higher order SVD to obtain core tensor factor matrices. Over here, one performs the power normalization on the spectrum. One can reassemble the tensor and then perform classification. And again, just on skeletons, such a simple pipeline on NTU can give you 74%. Without this power normalization, the results, from what I remember, drop to 60 or below. And of course, those ideas apply to CNN combinations. One can get very good results by using this notion of power normalization. We use the idea of second-order statistics in few-shot action recognition as well. So you can have support clips, query clip, pass them through C3D encoder, obtain blocks of features. One can apply temporal spatial attention, and again perform pooling, obtain second-order matrices, concatenate, and pass them through relation network. And the important message is again that the use of second-order pooling is better than, for instance, use first-order average pooling. Another example is few-shot object detection. So one can get ground truth bounding boxes, query image, pass them through some network, apply second-order statistics. And again, the story is very similar. The second-order variants outperform first-order variants. And finally, another example, self-supervised few-shot learning. So one can get images, one can design a number of pretext tasks, pass them through feature encoder. Over here, one applies second-order pooling, and then one can pass it to essentially to the classifiers. And again, if you look at first-order network, relational net versus second-order variant, there is a boost by just using those second-order statistics. So the conclusion is that they help, and they help actually in many tasks. But I think that those statistics are really connected to fine-grained recognition, because they deal with spotting really rare features, and I think this is the key in fine-grained recognition. So thank you very much. That concludes my talk. Thank you.